Hello and welcome back to another stream. Today we're doing something a little bit different. There was gonna be a collab today, but it got cancelled. It got cancelled. So I was sort of already not in the mood to read Ovid's Metamorphoses today. So in desperation to find something else to read, we are going to read today chemistry. This is a school chemistry textbook, and I've, of course, forgotten everything I know about chemistry since being in school. So you'll be at the same level I am, most likely. Bit of a shiny cover. I think this is, where's this from? I think this is probably from the 90s. Let's have a look. Let me have a quick look. Yes, this is from the 90s. So, might be. I don't know. I don't know too much about chemistry. Maybe it's somewhat out of date. But this isn't going to be a serious read. This is just sort of going to be just sort of like a reminiscence stream of remember school chemistry. And we'll skip the contents page. We don't need to be so directioned. Nor do we want the preface. Oh, but we do like introductions. We do like introductions. Let's zoom in and see how the brightness fares. Which way is focus? This way is focus? I think that way is focus. Oh, my pen, where's it gone? I'm always forgetting it. Excuse me. Hold on, I can move this a bit further. Chemistry begins in the stars. The stars are the source of the chemical elements, which are the building blocks of matter. I can move this a bit further. I wonder. The building blocks of matter, and the core of our subject. Within the stars, intense heat causes atoms of hydrogen, the smallest particles of the simplest elements, to smash together, merge, and become atoms of other elements, carbon, oxygen, iron, and the rest. This merging releases even more heat, which generates starlight. I've never heard the phrase starlight used before, but okay. So, starlight, including sunlight. See, I've heard sunlight before. Is a sign. Hold on, let me adjust my filters. One moment. Unos momento. Color correction. And we'll lower the brightness a little bit. Increase maybe gamma. No, that looks bad. Makes me look, that looks bad. Let me go to defaults on that. Do not adjust gamma. I can, however, adjust the brightness a little. And up the contrast a little. We'll see how we go. I can always turn that off if I like. Okie dokie. So including sunlight is a sign that the elements are still being formed. Ah, that makes sense. That makes sense, of course. The planet Earth is made up of elements forged long ago in ancient stars. Many millions of years after a star is formed and begins to cool, its outer layers may collapse like a falling roof into its exhausted core. This mighty quake, can you really call it a quake? I guess you can, produces such large shock waves that the star shrugs off its outer layers and sends them into space in a huge explosion called a supernova. 6 such explosions have been detected in our galaxy in the past 1,000 years. The most recent in 1987. The shock of explosion raises the temperature in the star even higher than before. The Crab Nebula, produced by the supernova of 1054, was visible in broad daylight for 3 weeks. At such high temperatures, even the bigger atoms collide violently enough to merge and become still heavier atoms. The very heavy elements now found on Earth, including uranium and gold, were made in this way. Changes, we shall come to know them as chemical changes, have taken place among the elements and have converted them into the raw materials we find on Earth. Thus, the elements formed in stars have become rocks, ocean, air, vegetation, and flesh. We humans have discovered how to change these raw materials into substances that are well suited to our particular tasks. In the early days of civilization, stone was replaced by metal as the material from which tools and weapons were made. At first, metals were blended together by accident. Then it was found that certain mixtures were easier to cast and mould, easier to use and more durable, and blending was done to achieve specific ends. How long's the introduction going to be? Not too long, probably. Well, we're gonna read very lightly. Well, you really can't see that image. I'm gonna turn those settings off because that will ruin the vibe. What is it that causes it? Is it contrast? Brightness? Yeah, see, there was people in that image. You couldn't even tell. Oh, big book, hard to get to the top of the page. Oh, okay, I will close my curtain just a little bit. Just a little bit. It's too bright. It's really too bright. That should be enough. We can always close it more if it's not. Of new materials, together with humanity's spirit of inquiry, eventually gave rise to science, the systematically collected and organized body of knowledge based on experimentation, observation, and careful reasoning. In particular, that spirit of inquiry led to the branch of science known as chemistry. Greed admittedly drove that spirit originally, for chemistry sprang from the alchemist's vain struggle to convert lead into gold. Although the alchemists failed to copy the stars, in the course of their failure, they discovered that they could achieve many other conversions of matter. For example, rocks into acids and fats into soaps. Thus they opened the road to modern chemistry. Chemists continue to discover through experiments, tests done under carefully controlled conditions, how to convert one kind of material into another. Their experiments, the way chemists collect and organize and use their observations and measurements are where we begin our journey. In the course of this journey, we shall meet the elements and see the combinations they form. We shall end it where chemistry merges with biology, with combinations of elements so elaborate that we regard them as being alive. That's a cool introduction. We probably won't bother with reading the rest of this introductory part, and we'll just sort of skim around aimlessly, and we'll do that for an hour or two. That's the plan. I'm not actually interested here in learning any chemistry. That would take far too long. I would like to one day. I will say I would like to one day, but not today. How do I want to do this? Let me look over here. We'll just sort of reminisce on the curious sort of things that are in chemistry. Let's get past the introductory parts. Yes, I remember doing the lab stuff was always so much fun. I remember I dropped one of these once. It didn't break, but I think I did some damage to it. And I was told, don't drop these. I don't recognize this though. A fractioning column. I don't recognize that. This apparatus. Hold on, let's zoom in a bit closer actually. In fact, let's bring the whole camera a little round so I can be more in the middle. What do we have here? This apparatus, used for fractional distillation, includes a fractioning column packed with glass beads. A small portion of the distillate is collected in a series of flasks, and the content of each is called a fraction. I assume this is it's the same sort of concepts they use in petroleum. The fractioning columns in an oil refinery work on a principle similar to that used in a laboratory, but on a much larger scale. So what's going on here? How does this work? Because there's only one output, unless they change it. You know, you get something boiling in here, it boils up here, and then it'll go through the condenser to condense down and fall into a thing. So what are these doing? Ah, perhaps, no, because these aren't connected at all. These aren't connected at all. It looks like you have to manually move it. You see, with the regular sort of you know, it's very common. It boils and the condenser goes into the thing, but here there's I don't know how. Maybe it'll give us a quick tips. You know, this is talking about separation. You know, and they've got a bunch of distillations on the other page. I wonder, can we focus a bit better than this? It's a bit blurry. Oh, we've already got to zoom in more. Infiltration. We shake the sample with a liquid and then pour the mixture through a fine mesh, the filter. The soluble material in the sample dissolves in the liquid and passes through the filter. The insoluble material does not dissolve, it is captured by the filter. We can use filtration to separate common salts from powdered glass, because salt is soluble, but glass is not. Crystallization is another technique used for separating and purifying. Oh, we have a nice picture of that, I think. No, that's not crystallization. That's just precipitation occurs when an insoluble substance is formed. Here, yellow lead iodide, which is insoluble, precipitates when we mix solutions of lead nitrate and potassium iodide. Ah, yes, now I understand. Crystallization is another technique used for separating and purifying the components of mixtures, because impurities, the other dissolved components, stay in the solution as the crystals form. This purification process occurs on a grand scale when ice forms from seawater. Sea ice is largely fresh water, because the salt remains behind in the ocean. That's fascinating. I didn't know that. I would have assumed. So I mean, of course, it will return back, but you know, that's fascinating. Does that mean that if you go to Antarctica, there would be comparatively, you know, maybe that makes yeah. I can kind of see it. You know, that's fascinating. The technique of distillation separates components of a mixture by vaporizing one or more of the components. Vaporizing. Okay. Well, yeah, it makes sense. Yeah, of course, you turn it into a vapor. Yeah, of course, that's what the word vaporizing means, of course. It can be used to remove water, which boils at 100 degrees, from salt, which boils at a much higher temperature and is therefore left behind when the water evaporates. Fractional distillation is used for separating components of mixtures of liquids that have different boiling points. Oh, that's how you do fractional distillation with that setup. Of course, each pot boils at a different temperature, so you're not separating it with the fractional column. Or actually, maybe no, I still not get it. Let's keep reading. Let's keep reading. That have different boiling points. The mixture is heated, and the rising vapor passes up for a fractionating column packed with glass beads. The vaporized component with the highest boiling point condenses on the beads near the bottom of the column and drips back down into the boiling mixture. The vaporized component with the lowest boiling point continues to rise through the column without condensing and passes out into the condenser. Therefore, the first fractions to be collected consist of those most volatile of the mixed liquids. When that component has all boiled off the sample, the next most volatile component comes through, and so on. Ah, now we understand. Giant fractionating columns are used to separate the various components of petroleum, ranging from the volatile fractions used as gasoline, between 50 and 200 degrees, and kerosene at much higher degrees. Now we understand. So I guess it's still totally manual. You've still got to move your things. It's not automated. What's this? We have a picture. What's the picture about? In paper chromatography, I did paper chromatography once in school. What was it about? Hold on, where's my water bottle? In paper chromatography, the components of a mixture are separated by washing them along a paper. The support with a solvent, a primitive form of the technique is shown here. On the left is a dry filter paper, which a drop of food colouring has been applied. The filter paper in the middle was spotted and then placed in solvent. What do you mean spotted? And then placed in solvent. The filter paper on the right has been allowed to dry after the solvent spread out to the edges of the paper, carrying the two components of the food colouring in different distances as they spread. The dried support showing the separated components is called a chromatogram. Interesting. Fractions used as devo. Of course, this was a side. The residue remaining behind after distillation is asphalt, which is used for paving highways. Here we go. Here's an explanation of chromatography. Chromatography is a separation technique that relies on the abilities of surfaces to adsorb or bind substances. There are various versions of the technique. In the simplest, the sample is washed out from the center of a disc of filter paper. Substances that are adsorbed most weakly to the paper move further than the others, and, if they are coloured, give rise to separate patches of colour on the paper. This appearance is the origin of the name chromatography, which comes from the Greek word meaning colour writing. Gas-liquid chromatography. In gas-liquid chromatography, the sample is vaporized and carried in a stream of helium, the carrier gas, through a long, narrow tube. The tube is coated or packed with aluminium oxide. Wait, hang on, is this an American book? Aluminum? Or maybe it is aluminum. No, hang on, this is surely a British book. Let me quickly have a look. America, printed in the US. Okay, American. We have aluminum. Aluminum how do you say it in American? Aluminum. I don't know. I can't do an American accent for one single word. That's madness. Aluminum oxide, or a similar adsorbent material, soaked in the station. Now, I wonder, this is adsorbent, right, and not absorbent? Like those are two totally different directions. Ab and ad. I assume it means adsorbent, but oh yeah, maybe. Um, soaks in the stationary phase, a liquid of low volatility. The component that is adsorbed least strongly by the stationary phase emerges first from the other end. As time passes, the other components of the other mixtures emerge. Each is detected electronically and signaled by a peak on a chart called a chromatogram. Ah, yes, I've seen these before. They're used in a bunch of stuff. Chromatograms. Although I'm mistaking it with spectroscopy, which is very different. That's what I'm mistaking it of. I remember I always forget how to do SI units. They're always it's so easy to forget, I think, when you don't use it for a long time. But it is easy to pick up, of course. It's a very, very convenient thing. Very convenient way of writing big and small numbers. Oh, we have a historical section. I like historical sections. They're always fun. What's this about? Is this going to be about SI units? This is John W. Lyons, Director of the National Institute of Standards and Technology. As we zoom in further, so read it. Scientists agree in many ways that we cannot really interpret an observation until we measure it or put a number on it. For most chemistry experiments and chemical applications, we express much of our data numerically. To do so requires measurements and measuring devices that I'm getting distracted, that determine the number of units or fractional units needed. If the measurement is to mean anything to other scientists, then we have to agree on definitions and values of the units. In other words, is this the guy who standardized the units? I thought it was a lot older than that. That the standardization of masses, lengths, and volumes began thousands of years ago is shown by the discovery all over the world of artifacts used as such standards, some dating from several millennia BC. Moreover, kings and emperors long ago established units of length based on the length of their own forearms, thumbs, and feet. In our work, however, we are much more precise than that. You know, for a stream like this, it'd probably be easier just to manually hold the camera and do away with the tripod entirely. Although I don't want it bouncing around quite so much. It bounces around anyway. This is a heavy book also. It's a school textbook. Of the many unit systems devised over the centuries, the one based on powers of 10 has become the international standard. This modern standardization began in 1791. See, I thought so. It's way older than I thought. When France adopted the meter as the standard unit of length. The term meter, in French, meter, gave rise to the common name of the entire system of units, the metric system. Hold on now. I thought it came from the Greek word metric. No, there is no Greek word metric, is there? Or is it matic? Whatever. Part of the impetus for the adoption of the metric system came from the work of the French chemist Antoine Lavoisier, who was at that time engaged in careful determination of the mass of a given volume of water. In due course, his work led to the first definition of the kilogram as the unit of mass. In 1875, 17 nations signed the Convention du Mita at Paris and established the Bureau of International something and measures, points and measures perhaps, to develop, maintain, and enhance the international system of measures. Now, 47 nations have signed the treaty, and all but 3 nations use the system in daily. America's not the one, is it? America's the one that's not on the list, isn't it? Properties extensive and intensive is a physical property that depends on the size of the sample. Is a physical property that is independent. Oh, I see. Terminology. Conversion. I remember I had a tough time with this when I did this. I never really got over it. It was always difficult. Multiplying and dividing with correct numbers. This book has a lot on the topic. Usually these kinds of books, they really gloss over that topic. Chinese dagger, 1000 BC. Look at that. Look at that. Nickel stills, known even in prehistorical times. The head of this Chinese dagger is crafted from a nickel steel meteorite. The dagger dates from the Zhou dynasty, 1000 BC. Look at that. That's crazy. That's crazy. What were you doing 1000 BC? I wasn't building daggers out of meteorites. It's kind of fascinating that they find it as a thing, where cool pictures. Atoms. Why is this real? Is this real, chat? The small dots are individual xenon atoms that have been arranged into the world's smallest advertisement. Advances in technique have only recently made pictures like this possible. Surely that's not right, really? I didn't know we could actually I didn't know we could even see atoms that clearly, let alone, I don't know, manipulate them. Surely that must be just a fake or something, surely. Maybe xenon is particularly malleable. The names of some elements are very ancient, because those elements have been known for a long time. The name copper is derived from Cyprus, or, well, what Cyprus would have been called, I expect, where the metal was once mined. The name gold comes from an Old English word meaning yellow. Elements identified more recently have been named in a more or less chaotic fashion by their discoverers. In some cases, the name refers to a characteristic property. Chlorine is a yellow-green gas, and its name derives from the Greek word meaning yellow-green. For other names, chemists seem to have turned poets. Vanadium, which forms attractively coloured compounds, is named after Vanadis, the Scandinavian goddess of beauty. Several elements are named in honour of people or places. These include Americium, Berkelium, Californium, Einsteinium, and Curium. The most recently discovered elements have not yet been given their final names and are known by temporary names such as unilenium for element 109, un standing for 1, nil for 0, and n for 9, until scientists agree on a permanent name. I was hoping they'd have a history part about the periodic table. They don't. They don't. The halogens. The halogens are colored elements. Chlorine, bromine, iodine. All metals can be deformed by hammering. Gold can be hammered into a sheet so thin that light can pass through it. Here it is possible to see the light through a sheet of gold. Ah, yes, look at that. You can see there's a candle behind the sheet of gold. That's crazy. I've heard that if you were to get transparent gold, it wouldn't be a gold color. It'd be like a sort of bluish color. I've heard that. That's crazy. See-through metal. A metal is a substance that conducts electricity. But what about non-conductive metals? Has a metallic luster and is malleable and ductile. Hold on, that's a terrible definition for metal. That's not what a metal is at all. You can find metals that don't meet any of these categories. Atoms can be discerned as bumps on the surface of a solid by the technique called scanning tunneling microscopy. This is an image of the surface of gallium arsenide. The gallium atoms are depicted as blue and the arsenic atoms as red. These are not their actual colors. The first pieces of experimental evidence for the existence of atoms were assembled in 1805 by John Dalton. You mean the James Bond actor? A scruffy but learned English school teacher, his atomic hypothesis was that all matter is composed of atoms, all the atoms of a given element are identical, the atoms of different elements have different masses. Doesn't say how he found it, though. Oh well. It kinda does. Oh, this is the guy who made the I guess the electron microscope. Eight 1981. Development of the 50 years after the development of the electron microscope, a new form of microscope was introduced by Gerd Binnig and Heinrich Rohr at IBM. The new microscope used electrons that tunneled across a narrow gap between two conducting surfaces. The introduction of this new type of microscope proved worthy of a Nobel Prize. In the scanning electron microscope, the source of electrons is a sharp tungsten tip, from which the electrons emerge as free particles. They form into a beam that threads through a series of plates containing small apertures. These plates, charged to a potential difference of several hundred kilovolts, form a lens that causes the electron beam that focuses the electron beam onto the surface under investigation. In the scanning tunneling microscope, the STM, the electron source is similar to that in the SEM, but the physical arrangement is much simpler. There is no electron beam, nor is there a focusing lens. I didn't know they were different technologies. I thought they were the same thing. Guess I was wrong. In the STM, the sharp tungsten tip is brought close to the sample and scanned over the surface. Huh. In a series of closely spaced lines similar to the scanning pattern used to form images on a television, the electrons travel across the gap between the tip and the surface with a potential difference of only about 1 volt. It's quite a lot, isn't it? Between tip and sample. The transfer is called a tunneling process because the electrons seem to burrow for a region where they should not be found. The tunneling current has been expected instead. The first experiment was fashioned to exploit the phenomenon, but the low degree of sideways spread of the electron current was a surprise, and the first experiments indicated that the tunneling current was confined to a single atom at the end of the tip. After the fact, the behavior is easily rationalized because the tunneling current decreases exponentially as the gap spacing is increased. The protruding atom on the tip closest to the surface totally dominates the tunneling current. As shown in the drawing, the current... What's that noise? I heard that last stream. Hello, Shark. I'm hearing noises. I'm hearing noises in my head. They're speaking to me. Maybe, I think it's birds on the sea. I think it's birds on the roof. How's it going? I was going to be doing a drawing today, but we're not doing drawing today. We're instead reading about chemistry. You gotta give the streamer dopamine. Very important. Yeah, but we got. So what's this image we've got? What's this image we've got? Perspective image of a 32 square nanometer region of the surface of silicon, showing the steps between the layers of atoms. The steps are 1 atom high. Oh, look at that! Look at that! It's a cool image. Silicon. Pure silicon. Are they? They look like way more than 1 atom step there. It looks like there's like 5 atom steps. Maybe. Looks cool. Looks cool though. What's this part here? At the bottom here. The nuclear atom. Experiments carried out at the end of the 19th century and earlier in the 20th century showed that atoms are made up of smaller particles. In fact, they showed that atoms have an internal structure made up of electrons, protons, and neutrons. Electrons. Just before the end of the 19th century, the British physicist J.J. Thomson. Do we have a picture of him anywhere? Maybe he's on the next page. I'm in figure 2.2, but I don't see figure 2.2 anywhere. Investigated the cathode rays that are emitted when a high potential difference, a high voltage, is applied between 2 electrodes in a glass tube. I read about this once. His observations confirmed... I read it on Wikipedia once. His observations confirmed earlier work suggesting that a stream of particles moves from one electrode, the cathode, towards the other electrode. These cathode rays caused a spot of light to appear when they hit a specially treated screen, and the spot could be moved by placing electrically charged plates or a magnet near the path of the rays Thomson found that the properties of the rays were the same, no matter what metal he used for the electrodes. Ah, here we go. We've got Mr. J.J. Thomson here. Look at him. Look at him. He looks like a scientist. Joseph John Thomson, who measured the ratio of the charge to the mass of an electron with the apparatus he used. Thomson showed that cathode rays are a stream of negatively charged particles from inside the atoms that make up the cathode. These particles, now called electrons, denoted E negative. The fact that electrons are produced regardless of the metal used for the cathode suggests that they are a part of the makeup of all atoms. Thomson determined some of the properties of electrons from the way the spot moved when he altered the charge on the charged plates, or the strength of the magnet. He measured the value of E over m, which is the ratio of the size of the electron's charge to its mass, and found it to be, I can't read SI, the letter C is the abbreviation for the SI unit of charge, the coulomb. The technological outcome of Thomson's discovery was the cathode ray tube used in television sets and computer monitors. This book is from the 90s. Each time we see a television picture, we are watching, and a sometimes more entertaining version of Thomson's experiment. Later workers, most notably the American Robert Millikan, devised experiments to measure the charge of an electron separately. Millikan found that E equals 1 to the power of negative 1.6 to the power of, I don't know how to read that, 10 to the power of negative 19. There's a way of reading it. C. Therefore, combining this value with the ratio determined by Thomson, we can calculate the mass of an electron as being a very small mass. This tiny value makes the electron by far the least massive of the subatomic particles of interest in chemistry. Nucleus. Does it say how they found the nucleus? Probably does. Actually, I don't want to bother reading about the history of the atom. Let's keep carrying on. I thought this was going to be a lot quicker than I thought, but actually I could have speed read a lot more. The masses of atoms. Gold foil. You can't see it up here. It's a diagram. It's a diagram of something to do with gold foil. By Geiger and Marsden. The alpha particles came from a radioactive source. Their deflections were measured by observing flashes of light, scintillations, where they struck a zinc sulfide screen. Most went straight through the foil with very little deflection. Fascinating. Mass spectrometry. We've got a diagram. What is the diagram about? A mass spectrometer used to measure the mass and abundance of an isotope. As the strength of the magnetic field is changed, the path of the accelerated ions moves from A to C. A to C. When the path is at B, the ion detector sends a signal to a recorder. At a fixed magnetic field, the three paths would represent the trajectories of the three ions of isotopes. Cool stuff. Cool stuff. Oh, we've got the guy. We've got the guy with the face. Avogadro. The moles. Molecules, compounds. Should have cut my fingernails. Whoops. Molecules. Ions. Cations. From the prefixes cat and an come from the Greek words for down and up. Oh yeah, like katadune. I was thinking, yeah, they got C there. I was thinking of C, but of course in Greek it'd be kappa. I really liked school. I gotta get the food. Take care. Oh, is this the Titanic? It is the Titanic. Chemical equations. I like these introductions. Add me on Discord or something. I have no idea what you're. I could probably find you somewhere. I don't know. I'm not in anyone's Discord. Maybe I'll go search up No Sharko. Chemists have developed a powerful language for discussing reactions in terms of chemical formulas and equations. The language which we explore here will allow us to grasp reactions into classes. I fetched the new Shaku there too. I see. Some of which we discuss in this chapter, as so often happens in science. The classification helps us recognize patterns that make the subject matter easier to understand and use. Moreover, once we have identified the different types of reactions that are likely to occur when substances are mixed or heated, we can begin to make predictions about specific cases. Cool. Oh, look at that type of. I wonder if this will be readable for us because we skipped half the book. But I remember learning about all these. These were fun. All different types of reactions. No, I remember I had to make a whole map of it, and I ended up doing it manually, but could have just googled it. There is like conveniently pre-made maps. Synthesis. Formation of compound from simpler starting materials. Decomposition. Formation of simpler substances from the starting material. Double repletion. Metaphysis. The exchange of partners. I see. I think Aristotle writes about that in a logical sense, not a chemical sense. Probably where they get the word metaphysis from. Combustion. Reaction with oxygen. To form CO2, H2O into another oxides of any other element. So it's any kind of. So what about oxidation? Isn't there a chemical process called oxidation? Corrosion. Reaction of a metal with oxygen to form the metal oxide. Sorry. Corrosion. Isn't that also oxidation? Reaction of a metal with oxygen to form the metal oxide. Based on the driving force of a reaction. Gas evolution. Formation of a gas. Precipitation. Formation of a precipitate. When one solution is added to another. Neutralization, the reaction between an acid and a base. Redox, transfer of electrons from one species to another. Simple example of a reaction is the formation of water from hydrogen and oxygen. The reaction is an example of a synthesis, a reaction in which a substance is formed from simpler starting materials. Another type of reaction is decomposition, in which a substance is broken down. An example is the reaction that occurs when chalk is heated to 800C. I see. I didn't know that. I didn't know that happened. It's probably got a common name for it. Thermal decomposition. Decomposition brought about by heat is typical of most carbonates. The driving force of this thermal decomposition is the escape of the gas from the solid calcium carbonate. Hang on, I'm gonna do something. I'm gonna remove the whole thing from the tripod. I'm just gonna hold it because I get the feeling that I don't actually need it. And just hold the whole thing. If I can get it in a comfortable position for myself. Maybe more interesting. Chemical reactions, the rearrangements of atoms present in the reactants. No, I remember balancing equations. That was tough. Or well, it wasn't. It was like the first thing you had to do. But I remember learning that. There's cool diagrams. I'm going to put down the thing. Probably not going to use it much. We defined an acid as a compound that contains hydrogen and releases hydrogen ions in water. Is that what an acid is? By definition. I mean, I would learn that at some point. Contains hydrogen and oh yes, because it's got like it's OH, isn't it? It's got like a yeah OH, oxygen and hydrogen, but probably more importantly the hydrogen. Wait, no, I think it's just the hydrogen because hydrochloric acid doesn't have oxygen in it. This definition was proposed by the Swedish chemist Svante Arrhenius toward the end of the 19th century. Oh, it's an old definition. And hold on. What do I twist the whole thing? No, I can't. Sorry, I'm fiddling with this camera, trying to figure out how I want it. Compound that contains hydrogen and releases hydrogens, produces hydroxide ions. Well, what have we got? We've got all different stuff. What have we got? We got the acidities of various household products can be demonstrated by adding an indicator, an extract of red cabbage, and noting the resulting color. Red indicates acidic, blue basic. From left to right, we have lemon juice, soda water rather, 7-Up, vinegar, ammonia, Drano, milk of magnesia, and detergents in water. Note that ammonia and Drano are such strong bases that they destroy the red cabbage dye, so no blue colour is visible. Fascinating. Is that where pH comes from? It comes from cabbages. The top 12 acids and bases. We got a top 12 list. Top 10 saddest anime deaths. The number 1 ranking acid in the world, the best acid, is sulfuric acid, lime, ammonia, phosphoric acid, sodium hydroxide, sodium carbonate, urea, nitric acid, terephthalate acid, hydrochloric acid, acetic acid, adipic acid. The uses of sulfuric acid have shifted over... Hold on, let me twist this whole thing up. Have shifted over the past 35 years from mainly industrial to mainly agricultural. Sulfuric acid. I have heard we use sulfuric acid in agricultural. I'm not sure what though, because you'd surely kill the plants with sulfuric acid. Maybe it's, I don't know. It probably does something. Here we go. Let's see what it says. Most sulfuric acid is now used to make fertilizers from phosphates, so its production is increasingly a measure of a nation's agricultural activity. Bases are too produced on an enormous scale. Ammonia ranks 6th in mass-produced among the industrial chemicals. However, it ranks 1st among the number of molecules manufactured. Fascinating stuff. The reaction between an acid base is the neutralization of one by the other to form a neutral compound, which is neither an acid nor a base. Sorry, this is a bit. We're doing, you know, hand cam action here. The Bronsted definition. Bronsted acid is a proton donor. That's the one I learned. Proton donation exception. I think that's the one I learned. Yeah. It was all about this sort of stuff, and there was a whole lot of stuff I had to learn about this. I remember this now. There was a lot of maths involved. See, I'm just here for the pictures. When bromine is poured on red phosphorus, the subsequent reaction is a redox reaction, which follows the same general pattern as a reaction with oxygen or hydrogen. Big explosion. Micrographs of the silver halide crystals in a photographic emulsion. Before and after development, the scale bar is 1 micrometer. Fascinating. Fascinating stuff. Copper reacts with dilute nitric acid to give blue copper ions and nitric oxide. When copper reacts with concentrate nitric acid, nitrogen dioxide is produced. the blue solution is turned green by this brown gas. Blue. It's blue. The activity series. I vaguely remember this. We've also seen that zinc metal can reduce copper 2+2 cations, however you're supposed to say that, to copper metal. However, it is also found that... No. Getting a text. It's getting darker now. We won't go too much longer then. We'll get to like maybe 1 hour 20 minutes. So let's speed through it then. Oh, look at this. Raw water goes in an aerator. Lime. Coagulants. Sludge. Sand. Charcoal. Potable water. You know, that's surprisingly primitive. I'm pretty sure that's basically the same filter we've been using for thousands of years. Stoichiometry. I always like that word, stoichiometry. What do we got here? The large round structures are the ammonia storage tanks in a modern plant for producing ammonia by the Haber synthesis, or the Haber synthesis. Quantities of hydrogen and nitrogen that must be supplied to produce a given amount of ammonia can be calculated by using the techniques here. Oh, fascinating stuff. I remember this. Oh, yeah, the yield calculations. Good times, good times. Calcium carbide is a dirty white solid formed from limestone and carbon. When, as here, water is poured on it, acetylene is produced. Once ignited, it burns with a brilliant white flame. The apparatus used for combustion analysis. I think I skipped a page. I remember titration. I actually really liked titrations, but they're like the thing everyone hates. Where you got the burette, and maybe the Americans call it Erlenmeyer flask. What did I call it? Was it just no? It wasn't round bottom flask. It was oh, what did they call it? What was this flask called? I can't remember. Can't remember, but yeah, I really liked titrations. Yeah, this brings me on to a topic I'd kind of hoped to actually bring up, but I never really got around to it. Was I really like this? Imagine this. Remember the titrations in class and all the other sort of lab chemistry stuff you had to do. Imagine that, but like a video game. and it's like 3D realistic graphics, POV. You got your hands come out like like this and stuff. And imagine a game of that, or all of this whole book, all of this stuff, and you just do chemistry. See, the thing is, like, the only time you can really do chemistry is in like school chemistry class, or if you go and become a chemist. There's a really quite limited options, or you could go buy the chemicals and stuff yourself, but it's kind of expensive. If your neighbours see it, you might end up getting the police called on you. It can be dangerous, so you got to get good stuff, and it's just sort of it's kind of inconvenient. It's inconvenient. The video game gets rid of all those inconveniences, but then don't just make it just a silly game. Make it real, or as real as you can code. And then force the player to have to do all this kind of stuff. They have to do all their maths, and they have to actually read a book like this to be able to do the game and win the game. That'd be a great idea, I think. Have them have to be able to do all this kind of stuff, like not in a bad way, but like it doesn't force you to do it in the game. But if you want to succeed, if you want to actually do the chemistry properly, then you need to do that. That'd be neat, I think. Oh, got the atmosphere. I contemplated between either this book or a book on geography, which would have had this kind of stuff in it, I think. Altitude. 100 kilometers high. That's so far. Troposphere. The stratosphere. I didn't know the temperature changed this much. Look at that. It really changes quite a lot. I didn't know it was so dynamic. I thought it would just sort of get colder as it went up, but it goes up and down. That's interesting. The atmosphere is divided into several regions. Oh, the gas laws. I can't remember what they are now, but I remember from the gas law stuff. All gases are transparent. Is that a definition? That doesn't sound like a definition to me. You can get I can't see through some of these gases. Most gases are colourless, but here we see three with characteristic colours. We've got brown nitrogen dioxide, pale yellow green chlorine, chlorine gas, purple iodine vapour. Here we go. We can finally learn how a mercury thermometer works, or barometer rather, not the thermometer. We will never know how our thermometer works. But someone was trying to explain to me how a barometer works, and I just couldn't figure it out. But now we will learn. In a mercury barometer, the presence of a column of mercury is balanced by the pressure of the atmosphere. I see. The height of the column is directly proportional to the atmospheric pressure. The space above the mercury is a vacuum, so it gives rise to no additional pressure made inside the barometer. I can kind of see that. That you got the hole here. Well, not the hole, but the vacuum, and then so the atmosphere will push down here, pushing up here, depending on the atmospheric pressure, which is how a barometer works. Oh yeah, they got arrows. I just noticed the arrows. Fascinating. So that's how it goes. Wow, look at her. She's holding a cube. The molar volume of an ideal gas at 0 degrees Celsius and 1 at ATM. I skipped what ATM means. Certainly not an automatic teller machine. Sulfur burns with a blue flame and produces a dense gas, sulfur dioxide. Well, it's getting really dark. We can barely see anymore. When carbon dioxide is passed over yellow potassium superoxide, they react to form colourless potassium carbonates and oxygen gas. Fascinating. Kind of looks like a thing. An explosion caused by the ignition of coal. Ah, I've heard this actually. I've heard that this is a thing that it was either coal. You can't get coal gas. That doesn't exist. But yeah, coal. It must be coal dust. Yeah, it's a really dangerous explosion, and it happens every now and then at coal storage facilities or something. Places that have coal going through them, and it's not like well maintained. Gas molecules travel at about the speed of sound. The reasoning behind this assertion is that sound is a wave of alternating high and low pressure carried through a substance by its molecules. Because the motion of the pressure wave depends on the speed at which molecules can move into new locations, we can expect the speed of sound in a gas to be close to the average speed of its molecules. The speed of sound is about 300 meters per second, so about 700 miles an hour. So we can expect average molecular speeds to be close to that value. The individual diffusion stages in the original U-235 diffusion plant at Oak Ridge. Hang on a minute. Oak Ridge? That's the Roblox game, the Oak Ridge nuclear power plant simulator. So I didn't know it was real. I thought it was fictional. Fascinating. Chlorine can be liquefied at atmospheric pressure by cooling it to negative 35 degrees. Liquid chlorine. Liquefaction of gases. At low temperatures, gas molecules move so slowly that intermolecular attractions may cause one molecule to be captured by another and stick to it instead of moving freely. When the temperature is reduced below the boiling point of the substance, the gas condenses to a liquid. The molecules move too slowly to escape from one another, and the entire sample condenses to a jostling crowd of molecules held together by the attractions between them. Fascinating. Keep it at a low temperature, then the boiling point of the substance. Chlorine, boiling point of negative 35 degrees. Comes into contact with a surface cooled by a solid carbon dioxide. Temperatures as low as negative 100 degrees can be reached by adding chips of solid carbon dioxide to diethyl ether. By making use of the relation between temperature and molecular speed between lower average speeds corresponds to lower temperatures. I'd hoped we would skim through the whole book, but I wasn't. I went slower than I thought because I thought the pacing would be a lot faster, and I had to get through the whole book in 10 minutes. So I deliberately went slower, but I should have gone faster. Enthalpy, calorimetry. You're winning? Oh, welcome back, No Sharker. We're near the end, actually. We're near the end. I'm going to go for another 2 minutes because it's getting really dark and I can't be able to turn my light on. But yeah, we're having fun. We're having fun. Like, look at these cool pictures. Look at these cool pictures. The thermite reaction is another highly exothermic reaction, one that can melt the metal it produces. In this reaction, aluminium metal is reacting with iron oxide, causing a shower of molten iron sparks. The decomposition of ammonium dichromate to chromium oxide is so exothermic that once ignited, it produces a miniature volcano. I remember having to draw this diagram, the bomb calorimeter. I remember having to draw this, and it wasn't this diagram, but one thing I really didn't like about some of these diagrams here to draw is that what's really essential. You know, what's really essential? Because some things aren't essential, like well, I can't think of anything in this, but here, the stirrer. The stirrer. Is the stirrer essential? Did you need to draw the stirrer? Now, I assume that you do want to keep the water moving, but would it make more sense to, instead of indicating a stirrer, because what if you didn't have a stirrer? What if instead you had a what's it called, like a stirring thing, you know, the thing they put in beakers, and then you have a magnet in the hot plate underneath it that stirs it for you. You don't use a stirrer, you use a stirring like pill or whatever. Yeah, what if it was like a spoon and not a stir? I mean, a stirrer is a spoon, but like, you know, what if you just held the whole thing up and you like shook it around? You just shook it around. And this is the sort of thing, like it's like no, look, to get, if you want to pass this class, you have to include the stirrer. It has to be a stirrer. I'm like, oh, you know, but like, does it really need to? You know, like how abstract do you need to be? You know, like do I need to draw the table? Because it's got to stand on a table, right? It's not going to float in a vacuum, right? But so of course you don't include the table because, you know, why would you? Because it's not really necessary to like the scientific concept. Thought that was a turd for a second there. Yeah, I'd hoped to sort of skim through this a lot quicker than I did, but I didn't pace it so right. So we're like no amount of the way through. You know? But we've reached 120 now, so we're gonna skip to a random page and see what we look at. Liquids and solids. Now we're really talking about poo. The calcite and the argonite phases of calcium carbonate. London forces. The nearly spherical shape of these beads of water on a wax surfaces arises from the effects of surface tension. The beads are flattened slightly by the attraction of Earth's gravity. Latex spheres produced on one of the space shuttle missions. Each one is a perfect sphere of diameter 0.01 millimeter, formed by surface tension in the absence of gravity. When the adhesive forces between a liquid and glass are stronger than the adhesive forces within the liquid forms the meniscus, shown here for water and glass. When the cohesive forces are stronger than the adhesive forces, the meniscus is curved downwards. Ah, you know, that does happen, doesn't it? Oh, this was the barometer we saw earlier, I think. For demonstrating the pressure exerted by the vapor of a liquid. Mercury. The height of... Alright. Alright. Yeah, I hear ya. Sorry, I'm deafening everyone. The height of a column of mercury is depressed by the vapor pressures of water ethanol diethyl. Fascinating. Oh, I hear. Alright, well, we've reached the end here. We've reached the end here. By the way, can we try this at home? This is the you can do anything at home. Everything is recommended to be done at home. Can we find anything funny? I'm going to find something more explosive or illegal. Hang on. We get yes, nuclear chemistry. You can definitely do this at home. All right, that's the end of that. That's the end of the stream. That was a bit of fun. That was a bit of a googling closest nuclear reactor. One of these days, I'm gonna live stream the Roblox nuclear reactor game. It's kind of fun. Alrighty, that was a bit of fun. Thanks for watching. Peace out.